Hello students, in today's lecture we are going to solve the differential equation by Frobenius method. In our previous lecture we learned about the regular singular point and irregular singular point of a differential equation. So let me remind you that lecture again. Here we consider a differential equation of the type, and we assume that if P1 or P2, if one of the given functions is not analytic at a point x equals to a, then that x equals to a is a singular point of the given equation. So then we consider a function of the form q1 of x, which is equal to x minus a into p1 of x, and another function which is q2 of x, which is equal to x minus a whole square into p2 of x. And for x equals to a, if q1 and q2 are analytic, that means that they goes to infinity, then those points x equals to a are known as a regular singular point. Otherwise they are irregular singular point. And now we are going to study the different solution of differential equation by a method which is known as Frobenius method. So here we assume that if x equals to 0 is a regular singular point of the equation, differential equation, which is d square y upon dx square plus p1 of x into dy upon dx plus p2 of x y, which is equal to 0. If x equals to 0 is the singular point of this equation, and we assume the series solution of this differential equation in this form, which is y is equal to x to the power m into a naught plus a1 of x, a1x plus a2 x square plus a3 x cube, and so on, are in the summation form, summation from k equals to 0 up to infinity ak x to the power m plus k. If we assume the series solution of this differential equation in this form, here the value of m is determined by first finding the second order differentiation of this equation, and then by putting y dy upon dx and d square upon dx square y in this equation. We will find d square y upon dx square, dy upon dx, and y, and we will substitute those values in this equation. After putting these terms in this equation and after simplifications, we will get the identity, and on equating the coefficients of lowest power of x in the identity to 0, we will get a quadratic equation in M, which is also known as indicial equation. Thus we will get two values for M. The series solution of this equation will depend on the nature of the roots of the indicial equation, and in that we will have different cases. In the first case, for example, Case 1. When the roots of the initial equation, which are m1 and m2, are distinct and not differing by an integer. That means that m1 minus m2 is not equal to 0 or a positive integer. For example, if m1 is half and m2 is 2. For example, in the first case, when the roots of m1 and m2 are distinct and not differing by an integer, the difference of these two is not greater than by unity. For example, if we get the roots of the initial equation to be different from one another and the difference between them is not greater than by unity, such as in this case, then the complete solution of this equation, of this differential equation, will be the complete solution. Then the complete solution is equals to C1 into y. This is for the first value of m, clear, plus C2 into y for the second value of m. The complete solution of the differential equation 1 will be the superposition of the individual solution for the given values of m, where C1 and C2 are constants. In the second case, case 2, when the roots m1 and m2 are equal, that is, if both are the same, then the general solution or the complete solution of the differential equation 1 will be written in this form, which is C1 y1 y for m1 plus C2 into the differential of y with respect to m for m1, because m1 and m2 are the same. In the third case, if the roots m1 and m2 are distinct, when the roots m1 and m2 are distinct, and they differ by an integer, Clear? That is, if m1 is less than m2. For example, if m1 is 3/2 and m2 is 5/2, so there is a large difference, that the difference between them is greater than unity. Or another case, if m1 is 2 and m2 is 4. So in such a situation, when the roots m1 and m2 are distinct and they differ by an integer, such as in this situation, then the complete solution will be y is equal to c1 y for the first value of m plus c2 into the differential of y with respect to m for the second value of m. And in the fourth case, when the roots m1 and m2 are distinct and differing by an integer, So making some coefficients indeterminate, making some coefficients indeterminate then the complete solution will be c1 times y for m1 plus c2 into y for m2. So these are the four situations. If we solve the differential equation 1, if we solve this equation and we get the indicial equation, and by solving that indicial equation we will get two values of m, and if these are the situations, then we will follow these rules to obtain the complete solution of the differential equation. Now we are going to solve an example for the first case. If we solve a differential equation and we obtain the roots of the indicial equation m1 and m2 and they are not differ by a unity, then we will obtain the complete solution by this method. Example. And case 1. So we are asked to find the solution, find the series solution about x equals to 0 if this is the singular point of the differential equation, which is 3x into d square y upon dx square plus 2 into dy upon dx plus y, which is equal to 0. Clear? So according to these rules, we will consider the solution of the equation in this form, and then we will find dy upon dx, d square upon dx square y, and then we will substitute those values in this equation. So let's start the solution. We have the differential equation, which is 3x into d square y upon dx square plus 2 dy upon dx plus y, which is equal to 0. Let this is equation number 1. Since we are given that x equals to 0 is a regular singular point, then we assume the solution of this equation in this form, that y is equal to summation over k, which is from 0 to infinity ak into x to the power m plus k. Differentiating it with respect to x, then dy upon dx will be equal to summation over k into ak into m plus k into x to the power m plus k minus 1. Clear? By using power rule. And similarly, again differentiating this equation, we will get d square upon dx square, which is equal to summation over k is equal to 0 up to infinity into ak m plus k times, this power will come here, which is m plus k minus 1 into x, the power will be reduced by 1, so it will become m plus k minus 2. Clear? So we have now a y, dy upon dx and d square y upon dx square. Now substitute these three terms in equation 1. By substituting these three terms in equation 1, we will get equation 1 will become 3x into summation over k from 0 up to infinity ak into m plus k into m plus k minus 1 into x to the power m plus k minus 2 plus 2 times summation from k equal to 0 up to infinity ak into m plus k x to the power m plus k minus 1 plus y. Y is summation over k from 0 up to infinity ak x to the power m plus k, and this is equal to 0. So here is x, 3x. When this x is multiplied with this x, so it will become m plus k minus 1. Therefore, this equation will become 3 times into summation over k from 0 up to infinity ak into m plus k into m plus k minus 1 into x to the power m plus k minus 1. Clear? Plus 2 times summation from k equal to 0 up to infinity ak into m plus k into x to the power m plus k minus 1 plus this term, which is summation over k ak x to the power m plus k. This is equal to 0. Now here we have the variable x to the power m plus k minus 1, and here also we have x to the power m plus k minus 1. So taking summation x to the power m plus k minus 1 common from these two terms, so this will become summation over k from 0 up to infinity. Here we are left ak is also taken out of the integral, is also taken common from the terms, because both of these terms contains ak. So here we are left m plus k into m plus k minus 1, and here this is 3 times this 3 plus 2 times m plus k and x to the power m plus k minus 1 plus this term, which is summation from 0 to infinity ak x to the power m plus k, which is equal to 0. Now in this expression we see that the summation term starts from 0 and it goes on increasing. Therefore, let this is equation number second. If in the first summation, in this term, if we put k is equal to 0, because the value of k starts from 0 and it goes on, if we put k is equal to 0 in the first term only, and the coefficient taking the lowest degree, the coefficient of the lowest power of x equal to 0. Let me write it here. The lowest coefficient, this is the coefficient, the coefficient of the lowest degree term is x to the power m minus 1 by setting k is equal to 0, by putting k is equal to 0 in the first summation. Only, and that coefficient is then equated to 0 and equating to 0. Let me explain it again. Here for the first summation only, for this term, we will substitute k is equal to 0 and then the coefficient of this term is equated to 0 like this. When k is equal to 0, so it will become a naught, because k is equal to 0, into 3 into m plus 0, it will become 3m, and this will become m minus 1 plus 2m. This is equal to 0. Clear? Or we can also write it as a naught into 3m square, 3m square minus m. Clear? This is equal to 0. Or a naught into m is into 3m minus 1. This is equal to 0. This is only possible if m is equal to 0, if we put m is equal to 0, because the right side of this equation is 0, so the left side must be 0. In that situation, if this m is 0 or this m is 1 over 3, this is only possible since, remember, since a naught cannot be 0, a naught cannot be 0, then we are only left that m is either 0 or m is 1 over 3. Clear? The next coefficient, the next coefficient of lowest degree term is obtained by putting k is equal to 1 in the first summation and k is equal to 0 in the second summation. of equation 2. Look here, which is the next lowest degree term, which is x to the power m. Look here, we put it k is equal to 0 and we obtained the two values for m, which is m equal to 0 or 1 over 3. Now the next coefficient of lowest degree term is obtained by putting k is equal to 1 in this summation. So it will become x to the power m, and here in the second summation by putting k is equal to 0, so it will become x to the power m. Therefore we will obtain it as, it will become a1, and similarly it will become a1. So it will become a1, this will become a1 into 3 times m plus k is 1, so m plus 1 into m, because k is 1, so 1 minus 1 0, plus 2 times m plus 1. So in the first summation we substituted k is equal to 1, and for the second summation, here k is equal to 0, so it will be plus a naught, and then we should equate it to 0. Clear? Therefore now this will be, by simplifying it, it will become a1 into, when this m and 3 is multiplied, so it will be 3m square plus, this will be 3m and this is 2m, so it will become 5m plus 2 plus a naught, this is equal to 0, or a1 into 3m plus 2 into m plus 1 plus a naught is equal to 0, or a1 is equal to, this is minus a naught or minus 1 upon 3m plus 2 into m plus 1 into a naught. Clear? Now to obtain a recurrence formula for all the remaining coefficients, we will substitute k, we will replace or put k is equal to k plus 1. We will replace k by k plus 1 in the first summation, and here we will write only k. So it will become by putting in order to get a recurrence formula, for all the coefficients. Put k is equal to k plus 1 in the first summation only, and equate the coefficient of x to the power m plus k m plus k is equal to 0. So let's see from equation number 2. If we replace in the first summation only k by k plus 1, so it will become m plus k only, and it will become a k plus 1. So look at equation number 2. This will be a k plus 1 into 3 times m plus k plus 1 into m plus k plus 2 times m plus k plus 1 plus ak, this is ak, and this is equal to 0, or simplifying it, or ak plus 1 into, multiply this 3 with this term and 2 with this term, so we will get m plus k plus 1 into 3m plus 3k plus 2 and plus ak. This is equal to 0. Or ak plus 1 is equal to minus 1 over m plus k plus 1 into 3m plus 3k plus 2 into ak. Clear? This gives by k equals to 0 for k equals to 0, so we will get a1, and it will be minus 1 upon m plus 1 into 3m plus 2 times a naught. As you see here, we obtained a1, so the same relation is obtained by this recurrence relation. Clear? By just putting the values of k, and for k is equal to 1, so it will be a2, which is now minus 1 divided by m plus 1, sorry, m plus 2 into 3m plus 5 times a1. Or if we put the value of a1 here, now put the value of a1, this value here, so we will obtain 1, this negative sign will become positive. 1 over m plus 1 into m plus 2 into 3m plus 2 into 3m plus 5 into a naught. And similarly, if k is equal to 2, it will give us a3, which is minus 1 over, here if k is equal to 2, this will be m plus 3 into 3m plus 8 into a2, because a2. And now if you substitute this a2 here, this value here, you will get a3 in terms of a naught, which will be equal to minus 1 over m plus 1 times m plus 2 times m plus 3 times 3m plus 2 times 3m plus 5 times 3m plus 8 into a naught. Now, as we obtained the two values for m, as here you see that we obtained either m is equal to 0 or m is equals to 1 over 3. Now let's check these coefficients for m is equal to 0. For m equals to 0, a1 will become this, a1 will become minus, this is 1 and this will be 2, so this will be minus 1 over 2 into a naught. Similarly, a2 will be equal to 1 over 20 a naught by putting m equals to 0 in this expression. So this is 1 times 2 times excuse me, 2 plus into 5. So this is 2 2s are 4, 4 5s are 20 a naught. And similarly, a3 will be minus 1 over 4 80 a naught. So the series solution for y, which is in the equation number here. Now putting all the coefficients a0, a1, a2, a3 and so on here in this expression, we will get the solution for y. So y will become, hence for m is equal to 0, y will become this is a0 here into 1 minus x divided by 2 plus x square by 20 minus x cube divided by 480 and so on. So this is the series solution of the given differential equation of this equation for the value of m equals to 0. Now for m equals to 1 over 3, that this is equation number 3. This is our first solution. Now for m equals to 1 over 3, so now substitute here for these coefficients m equals to 1 over 3. So we will get a1 is equal to minus 1 over 4 a naught. By putting m equals to 1 over 3 in this expression, we will get minus 1 over 4 a naught. And similarly from a2 we will get 1 over 56 a naught, and similarly a3 will be equal to minus 1 over 1680 a naught, and so on. So therefore the second solution, hence for m is equal to 1/3, the second solution of the differential equation first, the second solution of differential equation number 1 is y2. This is the first solution, and this is the second solution. y2 is equal to a naught into, here you have to substitute all the coefficients in this series here. Clear? As are in this equation. Clear? But here the value of m is 1 over 3, and we will get the solution. So this will be a naught into, sorry, this will be a naught into x to the power 1 over 3 minus 1 over 4 x to the power 4 over 3 plus 1 over 56 x to the power 7 over 3 minus 1 over 1680 into x to the power 10 over 3, and so on. So this is the second solution of the given differential equation. Now in the given cases, here we are told that the complete solution will be the superposition of both the solutions. So it will be, the complete solution will be the complete solution is in this form, which is y is equal to a times y1 plus b times y2, or here we have written c1 c2, or you can write a b, any constants, these are constants. So it will be y is equal to a naught, this solution, which is a naught into 1 minus x upon 2 plus x square upon 20 minus x cube upon 480 plus so on, plus b naught times, I have written here, this is this by b naught. You can also write it as a naught or b naught. I have written it just b naught into, take common x to the power 1 over 3 common from this series, so it will be x to the power 1 over 3 into, this is 1 minus, this is x upon 4 minus plus x square upon 56 minus x cube upon 1680 and so on. So this is the complete solution of this differential equation. We are given this differential equation and we solve it by Frobenius method, and by using the first case we obtained this solution. Thank you very much.